Allora, buongiorno a tutti. Good morning, everybody. Take a seat, please. It's my great pleasure to open this session because Eva, you know, but this is the first seminar that we have for 23. So you're opening our series of hospitality seminars. So you are the first one. Just a short note. As you know, today we will open this new series of seminars. We have talked about very seriously to have seminars of some outstanding speakers coming probably also from outside the country. And so we are very anxious in some way to hear seminars from the people that are working in Biogem, the young people and the less young people, because we have to full a long waiting list until the end of 23. And I know that most of the outstanding speakers coming from outside the Biogem is almost full, but is not full, the list of the speakers, internal speakers. And I urge you, all of you, to sign and to make in your calendar a fixed date where you can tell us what you are doing, what you will do, what is the project that you have. Just for internal communication. Now today we are very proud to have Eva with us. She's from Spain, from Madrid, I suppose.
Well, I work in Madrid.
You are working in Madrid. She's professionally from Madrid. I know from his CV that he's an expert in oncology and mostly in breast cancer. And she's addressing new therapy for the treatment of this important cancer. She has been invited by the group of Giuliano. And thank you, Pino, to suggest her name. And I know that the main sponsor is Rino. So I asked Rino to this studies. Welcome to Biogem, Eva.
Yes, Professor Caso.
On the microphone.
Okay. Can you hear me? Okay. Okay. For me, it's quite a pleasure and an honor to introduce Dr. Eva Gonzalez here. It was quite surprising when she answered me for the invitation and for the collaboration. And I'm happy to have her here just to show her data and her research activity. As Professor Cavasso said, she stays in Madrid and she works to end to CNIO. So I give you the word and thank you for your presence here.
So I think I have to go there.
No?
Because if I have to move from here,
you can try.
but it doesn't. This is what happened before.
Yes.
Sorry, but
it doesn't respond.
No.
Here. The same.
Yeah.
Okay.
We are in fact. I don't know when it does respond and when it doesn't. When you come, it doesn't. It does what you want. But when okay. Well, thank you very much, Rino and Professor Falco, for the invitation of being here, everyone, for joining us this morning and for this very warm and welcoming that I have had so far. And I'm looking forward to the rest of the day to discuss with you your science and what we do. So I will share, let's see, sorry, I will share with you the part of the work that we are doing in the laboratory. And I will focus mainly on the work that we have done. So let's see if I no. So do we see the screen like this? This is small for everybody. Okay.
It's fine. It's fine.
Yeah. Okay. So I will focus on the work that we've been doing on RANK signaling, which is we try to understand basically the normal mammary gland development. One of the main approaches in my laboratory, because the healthy tissue is much easier to understand than the cancer. Then, you know, the influence of this pathway on the tumor immune crosstalk. And there's some other area of research in the lab where we have been looking into novel targets and resistance to treatments more related with what we were discussing this morning in terms of heterogeneity and current breast cancer treatments that I will not have the time to discuss during the presentation, but I'm happy to comment with you what we are doing in that regard, mainly with PDX models and other Asian-derived models. So RANK and RANK ligand are TNF family members. They belong to the superfamily of TNF. The ligand can be a transmembrane or a solid. Both of them are active, and once they act on RANK, it can activate different downstream pathways, including NF-κB, P38, JANK, and in the main role of this pathway, or the best known role, is on the bone, where the activation of RANK signaling is essential for the differentiation, survival, and activation of the osteoclasts, that are the cells responsible upon resorption. And based on this key role, an antibody against the ligand called Denosumab was developed, and it was approved in 2010 into different formulations for the treatment of osteoporosis and bone metastasis. The antibody was developed in Amgen, where I did my postdoctoral research. But when I joined Amgen in Seattle, I was more interested in addressing all of this pathway in the mammary gland, no? And there were some insights into what this signaling pathway may be doing in the mammary gland, and I kind of fall in love with the mammary gland as a model system, because most of the development occurs after birth, so it's much easier to follow, and it can recapitulate many fundamental biological processes that are important in many other instances, and in cancer in particular, many discoveries are done in breast cancer and then they are translated to other tumors. So during the embryogenesis, there is this small ductal tree that, you know, it stays kind of quiescent until puberty. Then in puberty, under the influence mainly of estrogen and other hormones, this epithelial tree invades the fat pad. And then it kind of stays here with small variations during the estrous cycle until pregnancy, where the combined action of progesterone and prolactin gives to the formation of these milk-producing cells and lactation, which is the major role of the mammary gland and a unique feature of mammals. And this is a completely reversible system. So by the end of lactation, the mammary gland regress during involution and goes back to a stage that, you know, it looks like a virgin gland, but it's not exactly the same. There are some interesting recent findings on that. There are two main compartments in the mammary gland: the luminal cells, where you have cells that express hormone receptors, which are the hormone sensing cells, and they communicate towards other luminal cells, and the basal compartment, where the mammary stem cells reside, because these mammary stem cells are able to give rise to all the lineages in the mammary gland, luminal and basal lineage, during embryogenesis. Then postnatally, after birth, each of the compartments is maintained by its own progenitors. This was clearly demonstrated with lineage tracing models, and only under certain circumstances you can reactivate bipotency from the stem cell compartment. So my laboratory and others have been addressing what RANK and RANK ligand do in this setting, and we demonstrated that RANK ligand is a key mediator of progesterone, so in the mammary gland towards the luminal and the basal compartment. And so as I said, I will comment a bit on what we have learned during all these years about the role of this pathway in mammary gland development and breast cancer. What it was known when I started my postdoc was basically this phenotype of the rank null mice, that there was no lactation. And I generated this complementary model where you can overexpress rank. And what we observed was exactly the same. There was no lactation and the phenotype was more or less very similar. So that was a bit of a puzzle for some time. And with years, we have understand the reason. So this clearly demonstrates that you need a very tight regulation of the pathway at particular stages during development to get a functional mammary gland. RANK regulates proliferation and survival of the mammary epithelial cells, but also their differentiation capacity. And this is some of the functional assays that we did, where we saw that cells that have high levels of RANK from the RANK overexpressing mice have an increased ability to constitute a complete mammary gland, which is the key assay for in vivo stemness, but also have an increased ability of giving rise to colonies from the basal cells, but also from the luminal cells. So activation of RANK signaling enhanced stemness, which is this term that needs a general definition, but it may involve many things. And the other important finding that we got was that these mice that overexpress RANK, they develop tumors faster and more tumors. And what was more striking was that if we block RANK signaling, and we do that with this RANK FC, we can completely prevent breast cancer development. So that was a key finding, because it was known that RANK ligand was regulated by progesterone, but this was the first demonstration that it's a key mediator of a protumorogenic role of progesterone in the mammary gland that is fundamental for breast cancer initiation. And we saw that not only in this carcinogenesis protocol, but also in other oncogene-driven models that we use. These are the two very commonly used in the breast cancer field, the MMPV-mu and the polyomamidal T. So in both cases, if you inhibit the pathway either with pharmacologically or genetically, you get a delay in the tumor onset, decrease tumors, and decrease lung metastasis. So this was the first evidences that inhibiting RANK signaling, you can not only inhibit bone metastasis, which is dependent on the role of the pathway on the osteoclast, but you can inhibit metastasis to other sites, and in this case, the lung. So these results and in any other model that has been tested, including BRCA1 mutation models, open the possibility of using RANK ligand inhibitors for breast cancer prevention. And this is, Denosumab is in the clinic, and there are worldwide clinical trials, prevention trials for women with high risk of developing breast cancer, in this case, BRCA1 carriers, to see if this preventive treatment with Denosumab can be an alternative to mastectomies, for example, or which are way more invasive. So all this supported this protumorogenic role of the pathway, but we were also trying to understand better, the functionality once the tumors were developed and in the presence of oncogenes that are common in cancer. So we breed these RANK overexpressing mice with these oncogene models, the polyomamidal T and the neu. So we were really puzzled by this result, because you are not seeing it run. Basically, when you have the two oncogenes, and I'm calling RANK an oncogene because by itself, it accelerates tumor development. Mice spontaneously develop tumors, but when you combine the RANK with either polyomamidal T or neu, we got this phenotype. So the tumors need longer to appear. And so the image is more or less the same that if you knock out RANK there, and we were really puzzled for some time until it occurred to us to look at senescence. And this was no, actually the answer. So these increased levels of rank in the mammary epithelia will induce senescence in the luminal epithelial cells. And senescence plays this role acting as a barrier for tumor development. So it's protective in these early stages. And this was the reason why our tumors delay. So we thought at the beginning that it was the two oncogenic insults were too much, but in fact, only RANK overexpression in the luminal compartment is enough to induce senescence. We see that in the normal mammary epithelia, but also in the mammary epithelial cells. And this senescence is driven by P16, P19. From the two pathways that are important for inducing senescence, when we breed these mice with P16, P19 knockout models, we no longer have this difference in senescence. So the other thing that was important is that these RANK-induced senescence cells were very sensitive to navitoclax. So inhibitors of BCL2, such as navitoclax and others, were really, really efficient killing our RANK-induced senescence cells. And you may wonder, because this was also one of our concerns at the time. I was telling at the beginning that we had evidence that RANK induced stemness, and now I'm telling you that it induces senescence, and it doesn't seem to be the same thing. No, it seems a little bit contradictory. But in fact, what we saw was that this RANK-induced senescence was essential for the stemness that we have proved years before. And if we kill the senescent cells with navitoclax, this increased difference in stemness that here we measure with the ability of these cells to grow in suspension as mammospheres, it's gone. So there's something derived from the senescent cells that is allowing the stemness, no? And that's some ongoing projects in the laboratory, try to understand better how this is happening, no? If this is a paracrine effect, if this is a intrinsic effect on the senescent cells themselves. And the other thing that we saw is that despite these tumors in the double transgenic mice need longer to grow, once the tumors grew, they were more aggressive. So the tumors from the double transgenics grow faster and develop more metastases than those from the single mutants. So senescence had this protective role early on, but then it tended to be pro-tumorogenic, as many other evidences in the senescence field are coming. And these tumors from the double transgenic have many more of these double positive cells that express at the same time basal and luminal markers. These cells never exist in a healthy mammary gland in the adult. They are common in the embryo, but not in the adult mammary gland. But in this context of the tumors, and when we have the two oncogenes, they are more frequent. And so we should ask ourselves if the senescent cells were responsible of this difference. So we treated before the tumors appear, we treated the mice with navitoclax to eliminate the senescent cells. And what we saw is that we no longer had differences in tumor growth. So in fact, yeah, these senescent cells were responsible of fostering tumor growth, and it was responsible as well of this accumulation of double positive progenitor-like cells that were in these tumors. So this, with these results, when we try to see if what happened in the human setting, all of these are mouse models. We look at the TCGA, to signatures of high RANK expression, and we saw this nice association between high levels of RANK and senescence in luminal breast cancer, not in basal-like breast cancer, but in luminal. So it seems that RANK may be regulating senescence in luminal breast cancer as well. So this is kind of a wrap-up of this story. Where high levels of RANK-induced senescence in the luminal epithelia, which protects from breast cancer development for a while, but then once the tumors arise and escape senescence somehow, these senescent cells foster more aggressive tumors. And as I said, we now have more sophisticated models in the lab to try to address and pinpoint how this is happening. So I left you on the fact from the clinical applications of Denosumab on the clear role that RANK has on tumor initiation. But what we've been trying, and we are still working at, is can we actually treat women that already have breast cancer, no? Which is more of a problem than probably the prevention setting. And to try to understand that, we also use this polyoma middle T mouse model. And what we did was to wait until the tumors arise. In these mice, they need longer, but finally they got tumors. And when you look at the tumors, histologically, they are equally aggressive, and there's nothing major that you see at the histology. And then we transfer them in a wild-type setting. This was also because the knockout mice have many phenotypes, and that may influence breast cancer development and aggressiveness by themselves. So when we do this, we notice two things. One, that these cells need longer, the tumors to arise. I don't have the graph here, but you trust me. And then there is a decreased ability of these cells to give rise to novel tumors and novel metastases. So these are the tumor initiating cells, or the metastasis initiating cells. And there is a very clear reduction when the tumor cells do not express RANK. We did this at the genetic level, but also pharmacologically. So in the polyoma middle T model, these tumors express RANK by themselves. So we try to emulate here the procedure in the clinic somehow, where we treated the mice with RANK ligand inhibitors, which will be similar to the neoadjuvant setting before surgery. Then the women, the tumor will be removed. And there is this period where it's called a cool disease, where after some time, some women develop recurrence or metastasis. So some tumor cells are left behind. So we try to emulate this with a limiting dilution assay to kind of count how many cells do we actually have. And what we observed with this setting was that if we inhibit RANK signaling in this neoadjuvant setting, we can decrease the tumor initiating potential of these cells, while if we only treat in the adjuvant setting, it's not I mean, we don't get any clear effect. So this is, I think it will be important to consider when moving these findings to the clinic. And what we saw is that actually this inhibition of RANK signaling early on induced like tumor cell differentiation. So this is an staining for milk. So these tumor cells now become like lactating. So they go to a differentiating effect, like they are a normal mammary epithelia. And I think that that's amazing and has not been that well considered in thinking on cancer treatment. Most of the treatments are going for killing the cancer cells or avoiding proliferation, but the differentiation ability is also something that needs to be taken into account. So I will move now from the tumor cell intrinsic effects to what these tumors may change or shape the microenvironment. And when we characterize the expression patterns of RANK and RANK ligand in cancer samples, we notice that the receptor is expressed on the tumor cells, but also in the tumor-associated macrophages and other myeloid cells infiltrating the tumor, while the ligand generally is not very commonly found in the tumor. So this is very different to the normal mammary epithelia, where you have RANK ligand in the hormone-responsive progesterone receptor-positive cells. This is no longer the case in cancer. So the regulation of progesterone RANK ligand is completely changed. But we have some RANK ligand in the infiltrating lymphocytes. So we have been devoted to try to explore these links between the tumor cells and the immune environment, because it is unclear how RANK will regulate the tumor immune response. There are The pathway is as a TNF was first described in the immune system, and there were many papers supporting that it can induce tolerance, central tolerance, peripheral tolerance, but also reactivation of the immune response. So in the context of cancer, it's unclear what is going to be the main role, and it is very important because thousands in Denosumab for the treatment of bone metastases, but that may also change the immune response, and there's not so much understood about that. So the first thing that we did with our mouse models was to analyze the immune infiltrates, as many others, and we noticed that the tumors that do not express RANK have an increased immune infiltration. These are mainly T cells and CD8 positive T cells, and these CD8 positive T cells are responsible of the delayed tumor onset that we observed when we injected the RANK knockout tumor cells. So these cells, as I was telling before to you, that you had to believe me, here's the graph. So the tumors that do not express RANK need longer to give rise to palpable tumors, and are the CD8 positive T cells, the ones that are mediating this delay in tumor formation. The other thing that we show is that these tumors that do not express RANK are less infiltrated by neutrophils. So neutrophils are clearly immune suppressive in this setting, because if we deplete the neutrophils, now the wild type tumors need longer to appear, as long as the RANK knockouts. So these neutrophils are being immune suppressive, and in fact they were regulating the infiltration by the CD8s. There is not a major effect in the knockouts because there's very few neutrophils. But as you can see, as soon as you deplete the neutrophils, then you increase the infiltration by CD8s, and therefore you delay tumor development in the wild-type setting. So now we conclude that RANK expression is inducing immune suppression through the neutrophils. And if we inhibit RANK signaling, we may get an increase in the infiltration by T cells and by CD8 positive T cells. So at this time, we were recruiting patients for a trial that we have ongoing in the Catalan Institute of Oncology to try to actually characterize this effect of Denosumab in cancer, but we were still recruiting. But I knew that Christos Sotiriou at Brussels was running a very similar trial. It was smaller than ours. It was only 27 patients. And they had finished the trial, so I went to Brussels to contact him and share our results in the mouse models and see what they were observing in the patients. So this was the design of the trial. It was a window trial where the patients will receive 2 doses of Denosumab, and they were comparing the diagnostic biopsy with the surgery. This is early stage breast cancer, or are patients that get surgery as with no neoadjuvant therapy at all, and they were the only effect would be what Denosumab was doing. So what it was doing was what we were observing in our mouse model. So after these 2 doses of Denosumab, they observed this increase in the tumor infiltrating lymphocytes and CD8 positive T cells, exactly the same changes that we observe in our mouse models. So this was really, I remember when I saw the data for the first time, very reassuring, because when we work with mouse models, you never know. I mean, there are some limitations of what may be happening in clinics. And this was really important as well, because all these patients, except for one, are ER positive tumors. So they are luminal tumors, where generally they are cold tumors. So they are very poorly infiltrated by immune cells, and immunotherapies are not working at all. So this will open the possibility that treatment with Denosumab may prime these tumors for a better response to immunotherapy, and that's something we would like to pursue in the clinic. So far, we have only done it in the mouse models. And as you can see here, if we treat with RANK ligand inhibitors, there is not effect when RANK ligand is treated alone on tumor growth, but it improves the response to immunotherapy. In this case, these are CTLA-4 inhibitors. So no, that will be the goal, to see if Denosumab can be used as immunotherapy in luminal breast cancer. And I'm hoping at one point we can run this trial. But no, that's still ongoing. So all this will suggest that actually, there is a therapeutic potential of Denosumab in breast cancer. However, the big clinical trials that have been ongoing with Denosumab in the adjuvant setting, so these are trials with 3,000, 4,000 patients, phase 3 clinical trials where they were not run for these effects. They were run to the primary endpoint was prevention of bone metastasis, so Denosumab in the current indication. But for the first time, they were looking at the effect on the primary tumor and the disease-free survival. And as you can see here, the Austrian trial saw an increased benefit when Denosumab was added to endocrine therapies. So this is a trial where all the women were postmenopausal women going with endocrine therapies. And in this case, BCARE is a way more spread trial where there's all kinds of breast cancer, pre, postmenopausal, and different ER positive, ER negative. And although in the Austrian trial there was an increased benefit, in the BCARE that was not shown, not even in the postmenopausal luminal tumors. No? So there is still a question on why the results of these trials are so different. But what is clear is that there are additional markers are required for identifying the patients that may benefit from Denosumab in the therapeutic setting. And that's the last story I will share with you today. So this is the efforts that we've been doing to try to characterize the expression of RANK and RANK ligand in large clinical cohorts. So to analyze in the tumor and in the stroma, and also to see the functionality of the pathway on established breast cancer using patient-derived xenografts. So what we observe in these two large collections, so this is a collection that we generated at Idibel, and this is one that we analyzed in collaboration with Emad Raka at Nottingham University. So these are the very famous Nottingham primary series that they have a very, they are very useful because they have a very, very well annotated follow-up for these patients for many years. So there's, in total, we analyzed more than 2,000 tumors, and what we observe is that what I was telling you before, so the receptor is commonly found both in the tumor and even more in the stroma, whereas the ligand is very, very infrequent in the tumor cells and in the stromal cells. We can never forget that the ligand is soluble as well. So the source of the ligand may be soluble, and you cannot detect it by immunohistochemistry. And when we analyze other clinical parameters, we observe that the receptor is more frequently found in tumors that are ER/PR negative. So tumors from the triple negative subtype, there was no association with HER2. And this was exactly the same in the Nottingham primary series. So you can see that the results are very consistent in terms of the expression of the receptor. And as it has been shown before, high expression of RANK, or this is positive expression, is associated or tends to be associated with worse survival. This is somehow expected because if the receptor is expressed mainly in ER-negative tumors have worse prognosis. However, in this MPS series, because there are many samples, we could see that with a multivariate Cox regression analysis, that expression of RANK is actually associated with poor prognosis independently of ER expression, and it's even better than ER, tumor size, grade, or stage. So it's a question of potency, and that may go beyond ER negativity. Then, because the ER positive tumors and the ER negative tumors are so different, we wanted to analyze both cohorts separately. And as you can see here, while in the ER positive subset, we didn't see any difference. It's true that these Nottingham primary series are a very old collection, and RANK is a very tricky immunohistochemistry. So we know that we are subestimating the number of positive cases, and there is very, very few. So we will need to, we cannot rule out that there is a role in the luminal tumors. We will need to analyze more recent collections for the immunohistochemistry to be totally reliable. But in the ER negative tumors where the levels are higher, there is a association with poor prognosis. No, here is only a trend, but you know, there is a very clear difference between the two subsets. And when we analyze the pathways that seem to be related to rank expression in these two big groups, ER positive or ER negative tumors, we could do that because some of these Nottingham primary series are in metabric. So there is gene expression data associated. So what we look at here is which pathways are related with rank protein expression in the ER positive or in the ER negative. And as you can see, in the ER positive, most pathways are negatively associated with proliferation, which may be supporting this role of ranking senescence in the luminal tumors, while in the ER negative, the pathways are mainly associated with tumor metabolism. And I think that that's something very interesting, that this different role in the different subsets may explain the difference in prognosis that we are observing. So we went to another collection to validate these results. These are another collection in collaboration with EMAD, which are only ER negative patients, so 400 here. And this is a more recent, so it's more reliable, the staining. And again, we saw this now significant association of rank expression with poor survival in these ER negative tumors. And because most of these patients are treated with chemotherapy, we focus on the chemotherapy treated group, and this is again this poor association with survival. This is important because, as you know, the triple negative breast cancer or the ER negative is kind of a mix of everything, and a heterogeneous association there. We try to see associations with HER2, but the numbers are not high enough to be very, very strong, the association with HER2. So I think the most reliable data is with ER negative. And again, if we do this Cox analysis, we saw that within the ER negative subtype, rank is an independent marker of poor prognosis. And then we try to see functionally in the PDXs, is the pathway still active? Can we therapeutically target it? And so we analyze each of these lines, despite you don't see much, is one PDX where we analyze the expression of the receptor. This is gene expression, this is protein, and that are PDXs that we generated in my laboratory or that I obtained through collaborations through EuroPDX and other networks. And as you can see, the patterns of expression at the level of protein are very similar to what we got in the clinic. So there is more expression in ER negative. So we selected 3 tumors to work with the functional assays. This one expressed both the receptor and the ligand, and these 2 express the receptor only. So first we analyze activation of the pathway. So when we treat with rank ligand, we see that we can activate downstream targets. So the pathway is still active. And so we treated these mice in vivo, and we did RNA-seq to see pathways that were regulated. And despite the 3 PDXs are very, very different, there were multiple pathways in common, many of them related with metabolism. So this supports the associations that we were observing in the clinical samples, others related as well with inflammation, oncogene response, immune regulation. And we try to see if adding rank ligand inhibitors, so when we treat only with rank ligand inhibitors, the benefit, we observe benefit only in one of the PDXs, the one that express rank ligand as well. You see a very clear attenuation of tumor growth, and we saw a decrease in proliferation. In the other 2 models, there was not that clear, but what we observed always was increased benefit when combined with chemotherapy. So this will be the setting for the treatment of rank ligand inhibitors. It will never go alone. It will go in combination with the standard of care. And as you can see here, docetaxel alone in this setting is the red line, and the tumors, no, some of them do not even disappear with docetaxel, but when you combine with Denosumab or RANKL ligand inhibitors, the tumors not only disappear, but then they never recur. So these tumors finally, even those that have disappeared, will grow again. So I think that that's very encouraging. And then the other big classification that we did was, is there any difference between menopausal, premenopausal patients, postmenopausal patients? No? And this was really surprising, because everything that I was telling you, that RANKL ligand acts downstream of progesterone, and everybody in the field expected that RANKL ligand will be more effective in the premenopausal women because of the activation of all the sex hormones. But we got this surprising result where really expression of the receptor was only associated with poor survival in postmenopausal women. So this is the collection of IDIVEL that contains all subtypes. If we do it in the ER negative collection, we observe exactly the same thing. So we have validated this now in 4 different collections, and the results are very, very consistent. So really, RANK is associated with poor prognosis only in postmenopausal women in this setting. And you can see the differences here by the Cox analysis. So the hazard ratio for RANK, the red lines are the postmenopausal. This is univariate, this is multivariate analysis. But, it's an independent marker of poor prognosis in these postmenopausal women. So that's something that we, a big effort in the lab is now ongoing to try to understand better what may be going on. One of our hypotheses that is supported by this data is that when we analyze, we do the same with the metabolic series. So look at the tumors that express RANK and the pathways that they are associated. And as you can see, in the premenopausal setting, there is RANK expression, but there is no association with, these are mainly NF-kappa B activation pathways. Whereas in the postmenopausal, there is important activation of this NF-kappa B that we believe this is activation of RANK signaling. So the receptor is expressed, but it seems to be more active in the postmenopausal setting. It can also be inflammation-related signatures and so on, but this is actually what happens in the bone. So after menopause, when the levels of estradiol go down, the levels of OPG, which is the inhibitor of the pathway, go down, and that leads to activation of bone remodeling and osteoporosis after menopause. So we think that in the tumors, they may be happening the same, that you have increased activation of the signaling after menopause. And again, when we, in the ER negative subset, we get this association with metabolic pathways. That is something we are exploring now. This is it. So thank you all for your coming today, for listening to me. I'm happy to discuss other things. I would like to thank all the people in my laboratory, because sorry if I was very long, but I give you a big overview from the very beginning with all the people that was involved in Barcelona, in IDIVEL, now at the CNAO. So this is the current laboratory. This is the clinical team in IDIVEL and all the collaborators for these studies and many others. And the work without them will be impossible. So those are the first ones to thank, and thank you.